For over 50 years, pretty much our entire digital world has been built on just one element, silicon. It's been the quiet, unassuming bedrock of a revolution that literally puts supercomputers in our pockets. But that incredible era? It's now slamming into the hard limits of physics and economics. So, what's next? Well, to understand that, we first have to look at the principle that got us here.
The story of silicon really is the story of Moore's Law. It was this simple, almost elegant prediction that the number of transistors we could cram onto a chip would double about every 2 years. And as you can see, that relentless pace took us from a couple thousand transistors back in 1971 to, well, over 100 billion today. It's that exponential growth that made everything smaller, faster, and just unbelievably powerful.
But yeah, that reliable 2-year beat has started to stretch out to 3 years, sometimes even 4. All the easy gains are gone. We are now fighting tooth and nail for every single percentage point of improvement. And this slowdown brings us to the big question for this entire explainer. If silicon's amazing run is coming to an end, what materials and what technologies are going to power our future?
Okay, so to figure out what's next, we first have to get a handle on why silicon is stalling out. And it's not just one thing. It's more like a collision with 3 different, really fundamental walls that are stopping progress in its tracks. First up, there's the economic wall. Building a single factory, they call them fabs, to make the most advanced chips now costs over $20 billion. That is a staggering price tag. It means only a tiny handful of companies on the entire planet can even afford to play at the cutting edge. And that, right there, slows down innovation for everybody. Then we slam into the physical wall. At the 2-nanometer scale, transistors are so small it's hard to even wrap your head around it. We're talking just a few silicon atoms wide. At that point, the weird laws of quantum mechanics just take over. Electrons can literally tunnel right through the barriers that are supposed to control them, which causes leaks, wastes power, and creates errors. And finally, we hit the thermal wall. When you pack billions and billions of those tiny switches so close together, they generate an incredible amount of heat. As you can see, silicon chips just start to fail once they get past 150 degrees Celsius. This creates a huge performance bottleneck because even the fanciest cooling systems can't get the heat out fast enough, so the chips have to be forced to slow themselves down.
So how do we get around these walls? Well, the first part of the answer isn't about replacing silicon everywhere. It's about using specialized materials exactly where silicon fails the most. So let's meet the 2 rising stars of power electronics, gallium nitride and silicon carbide.
So what makes these new materials so special? Well, a huge factor, as you can see here, is something called the band gap. Just think of it as the energy hurdle an electron has to clear to get moving. Silicon's band gap is pretty low, and that's why it leaks power at high voltages. But now look at SiC and GaN. Their band gaps are almost 3 times wider. This lets them handle way higher voltages and temperatures. We're talking well above 200 degrees without breaking a sweat. And check out SiC's thermal conductivity. It's over 3 times better than silicon at getting rid of heat. It's a beast.
Now, while they both crush silicon in the power department, GaN and SiC have their own specialties. You can think of gallium nitride, or GaN, as the sprinter. It can switch on and off millions of times a second with crazy efficiency, so it's perfect for things that need to be fast and small. On the other hand, you've got silicon carbide, or SiC. That's the powerhouse. It's built to handle extreme voltage and heat, making it the undisputed champ for the really heavy-duty jobs.
And listen, this isn't some sci-fi future stuff. It's already in the products you use every day. You know that tiny but super powerful laptop charger in your bag? Yup, that's GaN. That extra range and faster charging you're seeing in modern electric cars? That's SiC, making the whole system more efficient. In giant data centers and solar farms, these materials are saving just enormous amounts of energy. The point is, this power revolution is already here.
Okay, but what about the brains of our devices, the actual computer chips? For those, the solution isn't just swapping in a new material, it's about a radical reinvention of the transistor itself. Let's take a look at how engineers are basically redesigning the foundation of computing.
For the last decade or so, the industry workhorse has been something called the FinFET transistor. As you can kind of see here, instead of a flat design, the part that electrons flow through, the channel, was raised up into a 3D fin. This let the gate, which is the on-off switch, wrap around it on 3 sides. That extra contact gave the gate way better control, and it was a huge leap forward in stopping that power leakage we were talking about earlier.
But even FinFET has its limits. So now the whole industry is moving to the next evolution, gate-all-around, or GAFET. So instead of a vertical fin, This design uses stacked horizontal nanosheets of silicon. And the magic here is that the gate material can now completely surround the channel on all four sides. It's like a 360-degree bear hug, which gives it the ultimate control and pretty much eliminates that wasteful leakage entirely.
And the results? They're just staggering. An early prototype chip from IBM using this GAFET design showed a 45% performance boost over the last generation. But here's the kicker. It did that while using 75% less power. This is the kind of massive leap that keeps Moore's Law alive, letting us have way more powerful devices that don't just torch your battery in 5 minutes.
This new architecture is a brilliant rescue mission for silicon. It really is. But it's still just a fix for an old material. So you have to wonder, what if we could go even further? What if the future of computing isn't just a better design, but a fundamentally better material from the ground up?
And that question brings us to the most promising long-term successor to silicon for logic chips, carbon nanotubes. These things are microscopic cylinders of carbon atoms, and they are projected to be up to an order of magnitude. That's 10 times more energy efficient than the best silicon transistors we can make.
So if they're so amazing, why aren't we using them right now? Well, for decades, they've had this one enormous manufacturing problem. And I think this MIT researcher put it best. Trying to get billions of these tiny tubes perfectly lined up on a wafer is like trying to cover an entire state in perfectly oriented dry spaghetti. It has been a nearly impossible challenge.
But very recently, researchers at MIT had a massive breakthrough. You see, their old methods in the lab took 48 hours just to get the nanotubes onto a single wafer. But by developing some new industrial-scale techniques, they cut that time down to just 150 seconds. That is over 1,100 times faster. It's the kind of leap that finally makes carbon nanotube chips a real commercial possibility.
So what does all this mean? What it shows us is that the future isn't about finding one new wonder material to replace silicon. Instead, the whole industry is adopting a new philosophy, a new guiding principle known as more than more.
More than more is all about moving beyond just shrinking transistors. It's about building a whole diverse toolkit for innovation. It means using specialized materials like SiC and GaN for the right job. It means fully embracing 3D designs like GAFETs and stacking smaller chiplets to build up. And it means investing in a whole ecosystem of future materials like carbon nanotubes for the challenges that are still to come. So yeah, the first 50 years of the digital age, they were built on silicon. But as we've seen, the next 50 aren't going to belong to just one single element. They're going to be built on a combination of clever architecture, specialized materials, and groundbreaking new science. And the real question that leaves us with is, what incredible technologies will this new toolkit make possible?